Imagine a star, much larger than our Sun, living out its life in the vast expanse of space. For millions of years, it burns brightly, fusing hydrogen into helium in its core. But all stars, even the most massive ones, have a finite lifespan. When a massive star exhausts its nuclear fuel, it faces an explosive end known as a supernova. In the final stages of a massive star's life, the core becomes dominated by iron, which cannot be fused into heavier elements without consuming energy. This leads to a catastrophic collapse. Within a fraction of a second, the core temperature skyrockets to billions of degrees Celsius, and the core itself shrinks to a fraction of its original size. This sudden collapse triggers a powerful shockwave that races outward, blowing off the star's outer layers in a titanic explosion. During this explosion, elements heavier than iron are forged in the intense heat and pressure. This is where many of the elements essential for life, such as gold and uranium, are created. The supernova not only produces these elements, but also disperses them across the cosmos, seeding future stars and planets. One of the most fascinating aspects of a supernova is the formation of a neutron star, or black hole. If the core remnant is between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star. These incredibly dense objects have a radius of only about 10 kilometers, but contain more mass than our Sun. If the remnant is even more massive, it collapses further to become a black hole, an object with gravity so strong that not even light can escape. Recent observations have provided new insights into these cosmic events. For instance, astronomers using the James Webb Space Telescope have detected the presence of certain molecules in supernova remnants, which were previously thought to be destroyed in the explosion. This discovery has significant implications for our understanding of the chemical evolution of galaxies. Moreover, the detection of gravitational waves from merging neutron stars has opened a new window into the study of supernovae. These ripples in space-time, first predicted by Albert Einstein, provide a unique way to observe the violent aftermath of these stellar explosions. By analyzing these waves, scientists can gain insights into the properties of neutron stars and the extreme conditions present during and after a supernova. One of the most intriguing supernovae observed in recent years is SN 2024X, which exhibited unusual brightness variations. This anomaly has led scientists to speculate about the presence of a companion star or perhaps a previously unknown mechanism in the supernova process. Such discoveries continue to challenge our understanding and drive the quest for knowledge about these cosmic phenomena. Supernovae are not just destructive events. They play a crucial role in the life cycle of the universe. They trigger the formation of new stars by compressing nearby gas clouds, and their remnants, rich in heavy elements, contribute to the diversity of planets and life forms. Without supernovae, the universe would be a much less interesting place, devoid of many of the elements that make up our world. In summary, a supernova is a spectacular and complex event that marks the death of a massive star and the birth of new cosmic structures. It is a testament to the dynamic and ever-changing nature of the universe, where destruction and creation are intertwined in an endless cycle.